For millennia, humanity gazed at the night sky, filled with wonder and questions. Where did our sun, moon, and the twinkling stars come from? How did this intricate system of planets, moons, and asteroids come to be? The answers, shrouded in cosmic mystery, seemed forever out of reach. Then came a revolution in thought, a shift from mythology to scientific inquiry. Scientists, armed with reason and observation, began to unravel the secrets of our cosmic neighborhood. The question of our solar system's formation became a captivating puzzle, one that would take centuries to solve. This quest for understanding led to the birth of the Nebular theory, a scientific framework that elegantly explains the origins of our solar system. This theory, now widely accepted, paints a picture of cosmic evolution, a story of gas, dust, gravity, and time, ultimately leading to the birth of our sun and the planets that orbit it. The nebular hypothesis, as it was initially called, emerged in the 18th century, a time when scientific thought was undergoing a profound transformation. It proposed a simple yet profound idea. Our solar system formed from a giant rotating cloud of gas and dust known as a nebula. This idea, radical for its time, challenged the prevailing notion of a static universe. It suggested a universe in constant motion, where celestial objects are not fixed but rather products of dynamic processes. The nebular hypothesis, though initially speculative, provided a framework for understanding the observed characteristics of our solar system. The orderly motion of the planets, their nearly circular orbits, and the fact that they all lie roughly in the same plane. These features pointed towards a common origin from a rotating disk. Imagine a vast cloud of gas and dust, remnants of ancient stars adrift in the cosmos. This nebula, cold and diffuse, was the seed of our solar system. Over eons, gravity, the architect of the cosmos, began to sculpt this cloud, pulling its particles towards each other. As the cloud contracted, it began to spin faster, much like a spinning figure skater pulling their arms in. This increase in rotation was a consequence of the conservation of angular momentum, a fundamental law of physics. The collapsing cloud, no longer a uniform sphere, flattened into a rotating disk with a central bulge. This disk, the birthplace of our solar system, is known as the protoplanetary disk. Within this disk, the seeds of planets were sown, ready to grow and evolve. Within the swirling chaos of the protoplanetary disk, a remarkable transformation began. Microscopic dust grains, remnants of ancient stars, collided and stuck together, a process known as accretion. These tiny particles, drawn together by electrostatic forces, formed larger clumps. As these clumps grew larger, their gravitational pull increased, attracting more and more material. Over millions of years, these clumps grew into planetesimals, kilometer-sized bodies that were the building blocks of planets. The inner region of the protoplanetary disk, closer to the nascent sun, was a hot and turbulent environment. Here, only rocky materials like iron and silicates could condense out of the gas, forming the building blocks of the inner terrestrial planets: Mercury, Venus, Earth, and Mars. Section 5. Accretion, building blocks of worlds. In the outer regions of the protoplanetary disk, beyond what is known as the frost line, temperatures were much colder. Here, not only rock and metal, but also volatile compounds like water, methane, and ammonia could condense into ices. These ices, along with rock and metal, provided abundant material for the formation of planetesimals. The planetesimals in the outer solar system grew much larger than their inner counterparts, forming the cores of the gas giants, Jupiter, Saturn, Uranus, and Neptune. These gas giants, with their immense gravity, swept up vast amounts of gas from the surrounding disk, forming their massive atmospheres. This process of accretion, the gradual accumulation of material, sculpted the planets we see today. Section 6. The sun ignites, a star is born. While planets were coalescing in the protoplanetary disk, a dramatic transformation was occurring at its center. The continued collapse of the cloud caused the central bulge to heat up immensely, reaching temperatures of millions of degrees. At these extreme temperatures and pressures, hydrogen atoms, the most abundant element in the universe, began to fuse into helium, releasing an incredible amount of energy. This nuclear fusion marked the birth of our sun, a star that would bathe our solar system in light and warmth for billions of years. The sun's ignition had a profound effect on the surrounding protoplanetary disk. The intense radiation pressure from the young sun blew away the remaining gas and dust that had not yet accreted into planets, clearing out the solar system and leaving behind the planets we see today. Section 7. Shaping our cosmic neighborhood. The birth of our solar system was not a peaceful event. It was a time of intense bombardment, as leftover planetesimals, asteroids, and comets collided with the newly formed planets. These impacts, some colossal in scale, left their mark on the surfaces of planets and moons. Our own moon is thought to have formed from a giant impact between the early Earth and a Mars-sized object. This cataclysmic event ejected a massive amount of debris into orbit around Earth, which eventually coalesced to form our lunar companion. The early solar system was a chaotic and dynamic place, but over time, things settled down. The planets cleared their orbits of most debris, and the solar system evolved into the relatively stable configuration we see today. Section 8. Cosmic Sculptors Kant and Laplace. The nebular hypothesis, though a compelling explanation for the formation of our solar system, was not immediately accepted. It took the work of several brilliant minds to develop and refine this theory. Immanuel Kant, a German philosopher, was the first to propose the idea of a nebula collapsing under its own gravity to form stars and planets. His ideas, published in 1755, were largely ignored by the scientific community at the time. Pierre-Simon Laplace, a French mathematician and astronomer, independently developed a more detailed version of the nebular hypothesis in 1796. Laplace's work, backed by his mathematical prowess, gave the theory more credibility and helped to popularize it among scientists. Section 9. Modern Confirmations. A theory proven right. The nebular hypothesis, initially based on observations of our own solar system, gained further support in the 20th century with advancements in astronomy and space exploration. Observations of young star systems in various stages of formation, using powerful telescopes, provided compelling evidence for the theory. Astronomers observed protoplanetary disks around young stars, confirming a key prediction of the nebular hypothesis. These disks, much like the one that birthed our solar system, showed signs of planet formation, with gaps and rings indicating the presence of protoplanets. The study of meteorites, remnants of the early solar system, also provided valuable clues. The composition of meteorites, their age, and the presence of pre-solar grains, tiny bits of dust that predate our solar system, all supported the idea of a nebula as the starting point for our cosmic neighborhood. Section 10. Beyond our solar system, the birth of other worlds. The nebular theory, once a hypothesis to explain our own solar system, has now become a fundamental framework for understanding the formation of planetary systems throughout the universe. The discovery of exoplanets, planets orbiting other stars, has revolutionized our understanding of planet formation. The Kepler Space Telescope, launched in 2009, discovered thousands of exoplanets, revealing an astonishing diversity of planetary systems. These discoveries showed that planetary systems are common in the Milky Way galaxy, and that the processes that led to the formation of our solar system are not unique. The study of exoplanets continues to provide valuable insights into the nebular theory, helping us to refine our understanding of the processes that govern planet formation, the factors that influence planetary diversity, and the potential for life beyond our solar system. Section 11. The enduring legacy of the nebular theory. The nebular theory, born from centuries of scientific inquiry, stands as a testament to the power of human curiosity and the elegance of the universe. This theory, once a radical idea, has revolutionized our understanding of our place in the cosmos. It has shown us that our solar system is not a cosmic accident, but rather a product of natural laws at play throughout the universe. It has provided a framework for understanding the formation of planets, the diversity of planetary systems, and the potential for life beyond Earth. The nebular theory continues to guide scientific exploration, inspiring new questions and pushing the boundaries of our knowledge. As we continue to explore the cosmos, we carry with us the legacy of this profound theory, a reminder that we are all connected to the vast cosmic tapestry, woven together from the remnants of stars that exploded billions of years ago.